The quest to unravel the mysteries of the universe has captivated human minds for centuries. One such enigma that has fascinated scientists and spiritualists alike is the search for the elusive God particle. Officially known as the Higgs boson, this subatomic particle played a crucial role in the standard model of particle physics. Its discovery in 2012 created ripples in the scientific community, as it was the last missing piece of the standard model. However, the model is not the final word or the theory of everything. There are many things that it cannot explain, and for that, researchers at CERN are hunting for signs of new physics, and they might have got one. Scientists at CERN have found a hint of a disagreement with standard model predictions while analyzing data of a rare Higgs boson decay. And according to many experts, these unexpected discoveries indicate the possibility of new physics at play. Join us as we dig deep into how new measurements of rare Higgs boson decay could break our physics. Before we talk about the Higgs, we have to know something about the standard model. The standard model was drawn together in the 1960s and early 1970s from the work of a cadre of pioneering scientists, but in truth its origins extend back almost 100 years earlier. By the 1880s, it was becoming apparent that there were positively and negatively charged particles produced when gases are ionized, and that these particles must be smaller than atoms, which were the smallest known structures at the time. The first subatomic particle to be identified, in cathode rays, was the negative electron in 1897 by the British physicist and subsequent Nobel Prize winner Joseph John Thomson. Then, in 1911, Hans Geiger and Ernest Madsen, under the supervision of the Nobel laureate Ernest Rutherford at the University of Manchester, performed their famous gold foil experiment, in which alpha particles, helium nuclei, were fired at a thin gold foil. Some of the alpha particles passed right through the atoms in the foil, while others were scattered left and right, and a small fraction bounced right back. Rutherford interpreted this as meaning that atoms contained a lot of empty space that the alpha particles were passing through, but that their positive charge was concentrated in a nucleus at their center, and on the occasions, an alpha particle hit this nucleus dead on, it was scattered. Further experimentation by Rutherford in 1919-20 found that an alpha particle fired into air could knock a positively charged particle out of a nitrogen atom in the air, turning it into carbon in the process. That particle was the proton, which gives the atomic nucleus its positive charge. The proton's neutrally charged partner, the neutron, was identified in 1932 by James Chadwick at Cambridge, who also won the Nobel Prize. So the picture of particle physics in the early 1930s seemed relatively straightforward. Atoms were made of two kinds of nucleons, in the guise of protons and neutrons, and electrons orbited them. But things were already quickly starting to become more complicated. The existence of the photon was already known, so technically that was a fourth particle. In 1932, the American physicist Carl Anderson discovered the positron, which is the antimatter equivalent of an electron. The muon was identified in 1936 by Anderson and Seth Nettermeyer, and then the pion was discovered in 1947 by Cecil Powell. By the 1960s, with the advent of fledgling particle accelerators, hundreds of particles were being discovered, and the scientific picture was becoming very complicated indeed. Scientists needed a way of organizing and streamlining it all, and their answer to this was to create the Standard Model, which is the crowning glory of the cumulative work of the physics community of that era. But although several scientists contributed to the formulation of parts of the Standard Model through the 1960s and 1970s, Glashow, Salam, and Weinberg shared the Nobel Prize for the current formulation of it in 1979. And before we talk about the nature of the Standard Model, it is important to say some things about the beginning of the universe. This falls under the branch of physics known as cosmology. Scientists believe the universe started with the Big Bang happened about 13.7 billion years ago. and we have compelling evidence for that. A good argument can be made that before the Big Bang, there was nothing. When I say nothing, I mean nothing. No black, no matter or energy, no space, no time, nothing. People can't imagine nothing because, by our nature of being something, nothing is outside of our experience. At the instant of the Big Bang, the universe was very hot and filled with an opaque soup of energy and subatomic particles. At that time, we believed there was only one force at work in the universe, not the four forces we experience today. The holy grail of physics is to take the four forces we experience today and discover the formulation that allows us to understand how that primordial single force disentangled into the four we see today. This is called the Grand Unified Theory and would unify general relativity and the Standard Model. The Standard Model now is well known as a theory of how the known particles, on the smallest measurable scales, interact, and in so doing, unifies three of the four forces that comprise the sum total of physical interactions known to humans. The three forces the Standard Model unifies are the electromagnetic force, weak force, and strong force. The electromagnetic force is quite familiar to us. It includes light, radio, and the entire spectrum of colors, those we can see and those we can't. That force is the reason that chemistry works the way it does, and it is the force that holds everything together in the macroscopic world we know. The weak force is responsible for radioactivity by enabling subatomic particles to decay, and the strong force is responsible for holding the nuclei of atoms together, even though the electromagnetic repulsion of protons compels nuclei to fly apart. Unifying these forces means that the Standard Model gives us an understanding that these forces are really only one force beyond a particular energy scale, and are differentiated in the world we're familiar with only because our part of the universe is cold. Cold means that our environment here on Earth today is much less energetic than the environment of the Big Bang, or the space around the accretion disk of a black hole, or other places and/or times in the universe where the energetic environment is very hot, enabling the forces to unify. This is like saying that all the colors that we see are really a single color, which, before they pass through a prism, is the color white. The Standard Model is probably the most tested theory that humans have ever produced. Some parameters of the model are known to greater precision than any other physical entities. The Standard Model is so good that it predicted, and we found, the three vector exchange bosons of the electroweak part of the theory. Seldom do human theories predict something as abstract as the three intermediate vector bosons. Gravity is the only force not unified in the Standard Model. Next, let's shift the attention to the Higgs. Imagine a universe where all fundamental particles zoomed around at the speed of light, massless and without the ability to form the building blocks of matter. This was the perplexing scenario physicists faced before the Higgs boson. The Standard Model elegantly explained the fundamental forces in most particles, but it lacked a mechanism to explain why some particles had mass, while others, like photons, didn't. The Higgs boson entered the scene as the answer. Physicist Peter Higgs predicted the Higgs boson in a series of papers between 1964 and 1966, as an inevitable consequence of the mechanism responsible for giving elementary particles mass. This theory suggests particle masses are a consequence of elementary particles interacting with a field, dubbed the Higgs field. And according to the same model, such a field should also give rise to a Higgs particle, meaning if the Higgs boson wasn't there, this would ultimately falsify the entire theory. But it soon became clear that discovering this particle would be challenging. When three theoretical physicists calculated the properties of a Higgs boson, they concluded with an apology.
We apologize to experimentalists for having no idea what is the mass of the Higgs boson and for not being sure of its couplings to other particles. For these reasons, we do not want to encourage big experimental searches for the Higgs boson.
It took until 1989 for the first experiment with a serious chance of discovering the Higgs boson to begin its search. The idea was to smash particles together with such high energy that a Higgs particle could be created in a 27-kilometer-long tunnel at CERN in Geneva, Switzerland, the largest electron-positron collider ever built. It ran for 11 years, but its maximum energy turned out to be just 5% too low to produce the Higgs boson. Meanwhile, the most ambitious American collider in history, the Tevatron, had started taking data at Fermilab, close to Chicago. The Tevatron collided protons and antiprotons with an energy 5 times higher than what was achieved in Geneva, surely enough to make the Higgs. But proton-antiproton collisions produce a lot of debris, making it much harder to extract the signal from the data. In 2011, the Tevatron ceased operations. The Higgs boson escaped detection again. In 2010, the Large Hadron Collider began colliding protons with 7 times more energy than the Tevatron. Finally, on July 4, 2012, 2 independent experiments at CERN had each collected enough data to declare the discovery of the Higgs boson. In the following year, Higgs and his collaborator, François Englert, won the Nobel Prize for theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles. This almost sells it short. Without the Higgs boson, the whole theoretical framework describing particle physics at its smallest scales breaks apart. Elementary particles would be massless. There would be no atoms, no humans, no solar systems, and no structure in the universe. But while this discovery was a landmark achievement, validating the Standard Model and providing a crucial piece of the cosmic puzzle, it has raised new fundamental questions. Its properties not only determine the masses of elementary particles, but also how stable they are. As it stands, the results indicate that our universe isn't in a perfectly stable state. Instead, similar to ice at the melting point, the universe could suddenly undergo a rapid phase transition. But rather than going from a solid to a liquid, like ice transitioning to water, this would involve crucially changing the masses and the laws of nature in the universe. The fact that the universe nevertheless seems stable suggests something might be missing in the calculations, something we have not discovered yet. As a result, experiments at CERN have continued to probe the Higgs boson. And as might have been expected, when scientists analyzed data obtained by new measurement at the CERN laboratory in Europe, they found a hint of a disagreement with Standard Model predictions. Accepted theory predicts that the Higgs boson can decay in several different ways, with each decay occurring at a different rate. Many of the predicted decays have been observed and their rates measured, and the data agreed well with predictions. However, one specific decay mode had not been observed until recently. This is the decay of the Higgs boson into a photon and a Z boson. Z bosons are very unstable, and they decay in a tiny fraction of a second. Theory predicts that for every 10,000 decays of the Higgs boson, 15 decays should be into a Z boson and a photon. Because Higgs bosons are themselves rare, finding this particular decay is very difficult. To improve the odds of seeing this rare decay, scientists combined data from 2 gigantic detectors, ATLAS and CMS. Together, we found evidence that we had observed the decay of Higgs bosons into Z bosons and photons, but much to our surprise, we found that the decay rate was much higher than expected. Their measurements said that this decay occurred about 34 times out of every 10,000 Higgs boson decays. This is 2.2 times the theoretical value. So, what could this mean? It could just be a statistical fluke. That kind of thing happens in real physics measurements. But it could also mean that researchers are seeing the first hints of unknown physics. Higgs bosons do not directly decay into a Z boson and a photon. The actual decay is a multi-step process. For example, one way this can occur is that the Higgs boson decays into a pair of very heavy particles called top quarks. After that happens, one of the top quarks emits a Z boson, and the quark merges with the other one, and they turn into a photon. The process is essentially a little loop of top quarks that separates the Higgs boson and the two decay products. This top quark loop is not the only way in which the decay can occur. Other particles can also form part of the loop. And this is one possible explanation for the observed excess of this kind of Higgs boson decay. It might be that there are unknown particles, ones that haven't been discovered yet, that also can form a decay loop. So, the observation of an excess of events in which Z bosons and photons are made could be the first hint that something unexpected is happening. Still, it's entirely too soon to make any claims that this observed excess is a discovery, and no such claims are made in the paper. First, we need to be sure that the observed rate isn't just a fluke, and the only way to do that is to take more data. Essentially, the fluke scenario is one you can easily reproduce. Take a completely fair coin and flip it 10 times. While you expect to get an equal number of heads and tails, it's possible to get 10 heads purely by chance. However, if you flip the coin 100 times, you're much more likely to get the expected 50-50 split. Maybe all that has been observed is a similar statistical quirk. So researchers will continue to analyze more data. The data recently published was collected between 2015 and 2018. Data taken in the following years will hopefully help resolve whether the observed excess was a statistical fluke or not. The amount of data remaining to be analyzed is about twice as much as was reported in the recent paper, so this question should be resolved soon. In addition, the CERN accelerator is being upgraded, and within a few years, scientists expect to record 30 times as much as has been so far. With that boost in data, we'll know if this recent measurement was the first glimpse of new physics or not. After all, the discovery of the Higgs boson represents a pinnacle of human achievement in the quest to comprehend the fundamental nature of the universe. It gives a concrete explanation for mass and expands our knowledge of particle physics. The Higgs boson is a fantastic laboratory for new physics searches. It has opened doors for more research and future avenues on particle physics to pursue. And now, with the release of the Particle Physics Project's Prioritization Panel, or P5 report, particle physicists have come together to chart a course for the next decade, and beyond that, addresses all of these issues while simultaneously creating a healthy environment for particle physics to thrive in the United States and the world for the next generation. Here's what everyone should know. As told, many of the puzzles we wonder about today, including dark matter, dark energy, the nature of inflation, the origin of neutrino mass, and the physics of the Higgs boson, very likely have their solutions imprinted in the earliest stages of our cosmic history. In order to attempt to uncover the solutions to these mysteries, we have to take a variety of approaches. Yes, there are the brute force approaches of building high-energy colliders with the greatest energies, detection sensitivities, and fastest rates of collisions possible. But there are also finesse approaches, such as searching for rare interactions and nuclear recoils, measuring the oscillations of neutrinos, performing cosmic observations that are sensitive to these ancient imprints, and developing new technologies and laboratory experiments to interrogate nature as never before. If we want to pin down exactly how nature operates, we have to ask the right questions in a clever enough way to compel it to give up its secrets. That's precisely what the P5 recommendations, at long last, get right. The goals of a scientific field like particle physics, at any point in time, are fourfold. To enable the science that's going to address the big questions of the time, asking nature the key questions in ways that, if we are lucky, will lead to an increase in our understanding. To strike an appropriate balance between theory, which strives to understand how different scenarios would change phenomena that we can observe and measure, and experiment, which makes those measurements. To pave a roadmap for future research and support future researchers, and to do it all in a way that serves various different aspects of the community, from large research collaborations to small experiments to technological upgrades and innovations and more. While the P5 report does strike a solid balance between these four competing priorities, the aspects that will be most exciting to most people are the major science efforts that have been designated as the highest priorities. At the intersection of particle physics and cosmology are the quantum imprints left on the largest cosmic scales by the final moments of cosmic inflation. While we've detected, measured, and are working on understanding the density and temperature fluctuations, also known as scalar modes, that inflation left behind, there's another type of fluctuations that inflation produces. Gravitational wave fluctuations, also known as tensor modes. All inflationary models predict the same spectrum of gravitational waves, but different models predict different amplitudes. The next generation efforts of measuring the imprints, or lack of imprints, of these gravitational wave signals on the radiation left over from the Big Bang, known as CMB-S4 experiments, are one of the highest priority science efforts recommended by the P5 report. Perhaps the largest particle physics endeavor that's taking place in the United States today is DUNE, the Deep Underground Neutrino Experiment. The goal of DUNE is to generate a particle beam composed of an enormous number of unstable particles known as pions, to allow those pions to decay, where they'll produce muons and muon neutrinos, antineutrinos, among other particles, to send these muon neutrinos and antineutrinos through the Earth, where they'll have the opportunity to interact with the matter within the Earth, and then to measure the neutrinos with a special type of detector known as a time projection chamber, which arrive at a distant destination. The reason scientists want to do this, and to do it with such large numbers of neutrinos to such high precision, is because neutrinos of one specific species, either electron, muon, or tau neutrinos, don't remain that same species as they propagate, but oscillate between those various flavors. This kind of long baseline neutrino experiment would represent a generational leap over all current efforts. And since the massive neutrino is the only known particle physics phenomenon that already goes beyond the standard model, it's a puzzle that compels us to investigate it further. It deserves a high-priority investment. One super smart decision made in the P5 report is to hold off on investing deeply in any one of the proposed next-generation colliders. Although the report recognizes the necessity of building a machine capable of acting like a Higgs factory to study this all-important standard model particle. Instead of shouldering that expense right now, they recommend supporting the technology development of various accelerator designs to see if there's an advancement that makes it clear one design is superior to others. Right now, there are three main classes of accelerator design under consideration. First off, a future circular collider, which would be a much larger ring than the Large Hadron Collider, and which could collide either electron, positrons, or hadrons, such as protons, leading to the highest energy collisions with the greatest new discovery potential. Second, a future linear collider, which would collide electrons with positrons, leading to a very pristine signal, but that does not push the energy frontier beyond current limits. And last, a future circular muon collider, which would collide muons with antimuons, leading to high energies and pristine signals, but with the lowest number of total collisions due to the unstable nature of the muon itself. While all of these options are expensive, a significant advance in energy gain per meter would strongly favor a linear collider, while an advance in muon luminosity would strongly favor the muon collider option, cleverly named a muon shot, in homage to the Apollo program's moonshot from the 1960s. Also, an incredibly high priority for particle physics is the construction of at least one G3 dark matter direct detection experiment. A lot of people erroneously think that these dark matter experiments have been failures, but that's simply not how science works. Science tells you where you ought to be looking. and experiments are the only way to find out what both is and isn't there when you look. Over the past 30 years, our sensitivity to any exotic, massive particle that would interact with normal matter has increased by a factor of 320,000, signifying the best null result in all of science history. The goal of these next-generation G3 experiments is to become so sensitive that they're detecting, as part of their known background, what scientists call the neutrino fog, which is what cosmic neutrinos caused by radioactivity within the Earth, and neutrinos emitted by the Sun will induce inside the detector. Although these experiments were initially motivated by the search for WIMP-like dark matter, such as in supersymmetric or extra-dimensional scenarios, it's important to recognize that this approach is capable of detecting much more than just those favored models of dark matter, including other heavy exotic dark matter candidates like Q-balls and WIMPzillas. Particle physicists are recognizing the failed and arrogant approach of assuming we know what dark matter is going to be, and instead are casting a wider, broader, and more general net, evidence that they're learning from the mistakes of prior generations. And as another important aspect of the future of particle physics, the community recognizes the vital importance of multi-messenger astronomy. Right now, there are 3 unique types of signals that can arrive from sources throughout the cosmos. Light, in all of its forms, from gamma rays to visible light to infrared all the way to radio waves. Gravitational waves, now detected by not just LIGO and Virgo, but also through pulsar timing, and cosmic particles, including in the form of neutrinos that can come from solar system, galactic, and even extragalactic sources. While the first 2 types of signals are mostly confined to the realm of astronomy, the ability to detect cosmic particles is of supreme interest to the particle physics community. At the South Pole lies the ice cube detector, the best in the world at detecting cosmic neutrinos that interact with the icy matter around it. IceCube has already produced our first galactic map in neutrinos and has found neutrinos from an extragalactic source, a blazar, or an active supermassive black hole whose jet is pointed directly at us. Upgrading IceCube to the next generation of scope and sensitivity will enable unprecedented study of neutrino properties and will enable the greatest multi-messenger astronomy program in history. As a bonus, if a supernova goes off within the local group, the next generation IceCube facility will yield untold scientific riches. All of this comes along as part of a balanced portfolio within a sane, sober budget. Particle physicists are not asking for a 10-fold or even a 2-fold increase in funding, but rather are keeping to an annual funding level from the U.S. Department of Energy that's between just $1 and $2 per year for the next decade. They are including support for early career scientists and many varied small experiments and projects, not just at national laboratories, but also at universities and research centers. And they're neither proposing a giant wish list of every project imaginable, nor demanding one ultra-expensive flagship project, but rather are trying to make targeted investments across a variety of efforts that give the physics community and the general public the greatest science bang for their buck. It cannot be overstated how important an investment in basic, fundamental research is for the scientific future of any society. This kind of investment always, over the long term, leads to greater economic activity and technological development, as well as scientific leadership in the world. The return on investment is staggering. But most importantly, the P5 report shows that particle physicists are finally learning from their past mistakes and aren't arrogantly over-promising discoveries about what might be out there beyond the frontiers of the presently known. There's a universe out there waiting for us to explore it. With the path laid out in the P5 report, particle physics just might have a bright future in the United States after all. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.